Yeah, thank you so much. And thanks to the organizers for having me here. Today I'm going to tell you a story about two of my favorite families of polynomials coming from Schubert calculus land and how to change bases between them in a couple of different combinatorial ways. So this story, it starts with the six-vertex model, or at least that's a big part of it. And I know that there's a variety of people from absolute experts in the six-vertex model to graduate students who are coming from maybe the other side of this conference. So I want to just make sure that we're all on the same page. So why is ice in the title? Well, ice, if you're trying to think about how ice freezes, it's too hard to do 3D ice, and so instead we make an approximation, and we think about how if ice was two-dimensional, it would freeze in the plane. And so when these water molecules freeze, they have 6 different sort of configurations that they can wind up into, and then they arrange themselves neatly into some sheet of ice. And so we could draw these H's and O's and these dashes, or we could code this in a different way. And we tend to code it with the six-vertex model. So what's going on here is we have kind of a game board grid, and then we have some boundary vertices. And at all these interior vertices, we want to make sure that we have 2 arrows going in and 2 arrows going out. And that 2 in, 2 out restriction, it gives us 6 different types of interior configurations that we can have. So that's why this is called the six-vertex model. And then along the edges, we impose some boundary conditions. So the boundary conditions I've imposed here, sometimes they have a fancy name, domain wall boundary, but we just have these arrows pointing out for the top and the bottom and in for the sides. And so you look at all the different ways you could possibly fill in these arrows on this game board grid to fill out one of these configurations. And then there's just a nice sort of one-to-one correspondence between different types of molecule configurations that you can have and the different types of interior configurations that you're seeing. Okay. And that's a lot of arrows. We could draw less things by just deciding, well, the only important information is which arrows go left and which arrows go down. And if we know which arrows are going left and which arrows are going down, of course, we can reconstruct which ones were going up and which ones were going to the right. And so we do this, we just sort of highlight those arrows, and then instead of arrows, we can draw some squiggles. And again, it's the same sort of thing where we end up with 6 different types of building block tile pieces. And then each of these 6 pieces are going with one of these internal configurations. And then the boundary conditions force us to have things sort of starting down here and ending over here. And we can interpret this as really a tuple of sort of we'll call them pipes. So Bumpless pipe dreams, sort of coming from a different approach, Lamb, Leash, and Mazzone defined these objects because they were the right objects for something they were studying in Schubert calculus. So they defined them really from this perspective to be just a tiling of the n by n grid with these tiles so that pipes start at the bottom of the grid and end at the right. And they're called bumpless because later we'll see objects that look like these, but they got a bunch of bumps. So these are the ones without bumps. And then another sort of object that these things are in bijection with, of course, are alternating sign matrices. So an alternating sign matrix is just a square matrix with entries in the set -1, 0, 1, so that within rows and columns, entries sum to 1, and then the non-zero entries in each row and column alternate in sign. So we see this alternation going on here. Starting with 1, we don't care about the 0, we've got a -1, we've got a 1. And then those entries sum to 1. Okay, so alternating sign matrices, it's well known that they're in bijection with the six-vertex model. We can also think of this sort of pipe picture and just these all turn into 1s, these turn into -1s, everything else is a 0. So kind of these elbow tiles are governing what the matrix should look like. And from those, this bijection is claiming that we can always work our way backwards and reconstruct this picture. Okay. So it's a bijection. And here I've lined up a bunch of bumpless pipe dreams with their alternating sign matrices. Notice most of these, for these 3x3 pictures, are permutation matrices. And then there's this one special one with a -1. Okay, so how are we going to use these objects? We're going to use them to study something called Schubert polynomials. And again, this is coming from the Schubert calculus world. So what's our setting? If you're like not a geometer, well, here's just like the broad strokes of what's going on, but soon there will be more pictures and more polynomials. So Schubert polynomials, we're in this setting where we're trying to study the complete flag variety. So as a space, we can think of this as invertible matrices modded out by the Borel subgroup of upper triangular matrices. And within this complete flag variety, there's this special distinguished family of subvarieties called Schubert varieties. And Schubert varieties play a very important role because each Schubert variety gives rise to a Schubert class in the cohomology ring. And the Schubert classes form a linear basis for this ring. Now, if you're like not someone who likes to take products of classes in cohomology ring, well, good news, by Borel's isomorphism, we can represent this cohomology ring. We can present it as just a quotient of a polynomial ring. So we're just modding out by this ideal generated by the non-constant elementary symmetric polynomials. And then, well, we have like some sort of weird quotient thing going on, and so we really want a representative for the image of the Schubert classes, and these are the roles that Schubert polynomials are playing. Lascaux and Schutzenberger, they said, here's a nice set of representatives for the images of the Schubert classes, and we'll call these Schubert polynomials. Schubert polynomials, a lot of you in the room like Schur polynomials. Schubert polynomials are just a generalization of Schur polynomials. Every Schur polynomial is actually a Schubert polynomial for some permutation. And yeah, these are, sorry, I should have said indexed by permutations. If you're talking about the flag variety with n by n matrices, you've got permutations in Sn. Okay. So the initial definition for these polynomials that Lascaux and Schutzenberger gave was in terms of divided difference operators, where you start with some initial condition and then you do something recursive. But subsequent work led to a very vast combinatorial theory of a lot of different ways that we can write down Schubert polynomials using combinatorics. But here, just so you have a picture in your mind, here's the Schubert polynomials for S3. This is a math frac S. They look a little funny because I don't know. I'll confess when I'm like writing Schubert polynomials, I tend to be lazy and do a Roman S. But these should be math frac if they were typeset. But we start from this initial condition where we just have some staircase monomial, and then we apply our divided differences down. And you'll notice it doesn't matter whether I took sort of this path, like doing 1, 2, 1, or this path, 2, 1, 2, I got the same thing in the end. And that's not a fluke. It's a fact that the Schubert polynomials satisfy the same braid and commutation relations as the simple reflections do. And so this is a well-defined family of polynomials. The divided differences satisfy those same braid and commutation relations. It's also, this is like a tiny example. We only have one that's not a monomial. But they have non-negative integer coefficients. And so that gives us a hope of finding combinatorics to help us write these polynomials down. Okay, so the first bit of combinatorics we're going to see is how to use bumpless pipe dreams to write these polynomials. So we need an additional definition. We need to throw away some bumpless pipe dreams. A bumpless pipe dream is reduced if pairwise pipes cross at most one time. So here I've written down a non-example because, well, you can see like we're thinking about traveling along this pipe and like these two cross here and then they go back and they cross each other again. For us, for writing down Schubert polynomials, that's no good. We don't allow that. But then what we do, the theorem of Lamley-Chamizono, is that the Schubert polynomial is a weighted sum over reduced bumpless pipe dreams that trace out your fixed permutation W. So let's unpack this a bit just by example. So how do we get the weight monomial for each of these objects? We just look at the blank tiles in the picture. So here there's one blank tile in row 1 and one in row 3, so we get an x1, x3. Here there's 2 in row 1, so we get an x1 squared. So a very simple way of associating a weight monomial. And then how do we pick which bumpless pipe dreams go with which permutation? Well, we just we follow the pipes. So we label along the bottom with the numbers 1 through n, and then we trace where the pipes go. And this gives us a word in one-line notation if we just shift the word around a little bit. And so we just take the bumpless pipe dreams that trace out our permutation W and sum up their weight monomials, making sure that they're reduced. Pairwise pipes cross at most once. Okay, questions so far? Okay. So another nice thing about bumpless pipe dreams is that we can use these sort of local moves, these droops, to find all of our bumpless pipe dreams. So I'm not going to be very precise about what these droops are. I'm just going to give you a picture in your head. But we can always start from an initial bumpless pipe dream called the Rothe bumpless pipe dream. And this, if you know Rothe diagrams of permutations, this is literally the Rothe diagram, but I've drawn this a little curved instead of a straight edge. Here, for instance, we have 4, 2, 6, 1, 3, 5. So you can really see the permutation matrix hiding inside of that picture. And then you just take these pipes and you start to droop them down. So for instance, I have a blank tile here, and I can just bend this pipe a little bit and droop it to there. There's more rules, but that's the vague idea. Okay. There is another formula for Schubert polynomials. Again, it looks like a bunch of squiggly pipes. This one, it predates bumpless pipe dreams, which I'm going out of historical order a little bit, but these things are called pipe dreams. So again, we have a sort of tiling of the n by n grid, but now we have these 4 tiles. So we have some blanks. The blanks are no longer important in this story. They're just filling out the space down here. We have above the main antidiagonal, we can place sort of freely these bumps or these crosses. And then on the main antidiagonal, we just flesh it out and put these little hooks here to make an honest to goodness sort of planar history that we can trace out. So in a similar way, we get a permutation. We write 1 through n now on the top. We trace out where the pipes go, and we look at what permutation we get in one-line notation over here. Reading from top to bottom. And then we get a weight monomial in a similar but slightly different way. Now the crossing tiles are the important thing for our story. So here I have 3 crosses in row 1, I have 2 in row 2, and 2 in row 3, and so this gives me this weight monomial. I'm listing some names depending on how you look at these objects. There's a rich history to create the objects of pipe dreams. But Fomin and Krylov drew these nice sort of squiggles. Bergeron Billy transformed work of Billy Jockish Stanley to sort of turn a more array version into these pictures. But the big picture is that Schubert polynomials are a weighted sum over reduced pipe dreams for W. So this reduced condition is the same as before. Pairwise pipes cross at most one time. Okay, so we have 2 formulas. Oh, yeah, okay, there's these ladder moves that you can do. Again, you can start from an initial pipe dream, and you can iterate some moves to generate the rest of them. And these are Bergeron and Billy's ladder moves. Okay, so there's 2 formulas. We should be able to compare them and sort of see, they're giving the same polynomial. So in this very silly case, I've just lined up the things that have the same weight monomial. But generally, there will be lots of things with the same weight monomial, and you have to decide, how am I going to pair up a pipe dream with a bumpless pipe dream? What things belong together? And really answering that question, Gao and Huang, they gave sort of a canonical bijection between these 2 different objects. They basically said any nice bijection that is satisfying, is respecting some multiplicative structure of these polynomials is going to be the same bijection. So there's basically, you could theoretically pick many bijections, but there's only one nice one that like respects the multiplicative structure of these polynomials. So here, if you've got just x's floating around, this is great. There's richer versions of Schubert polynomials where now you've got some y's floating around. The y's are now recording information about rows and columns. So here, this x1 minus y1 is telling me there's a crossing there. This x3 minus y1 is telling me there's a crossing there. So if you take this richer version of Schubert polynomials, you'll notice that there is no weight-preserving bijection that preserves the whole product of binomials. So it's a bit more subtle to try and think, well, if I really care about the x and y weights simultaneously, why should these formulas be the same? Something a bit more mysterious there. But if you just want the x weights, it's all great, thanks to Dowji and Evil. Okay. All right, so those were Schubert polynomials. There was another family of polynomials in the title of this talk, Grothendieck polynomials. So Grothendieck polynomials are sort of K-theoretic analogs of Schubert polynomials. Schubert polynomials, we didn't see very many examples, but all of the examples we saw were homogeneous polynomials. That's generally true. The degree of a Schubert polynomial is the Coxeter length of the permutation. Grothendieck polynomials now can be inhomogeneous. But the lowest degree terms of the Grothendieck polynomials are Schubert polynomials. So it's like this family of polynomials that is encoding strictly more information than Schubert polynomials. Okay, so again, there's some sort of like, we start from an initial condition. The initial condition is actually like the same as the one we had in Schubert polynomial world. But then we have a more complicated divided difference operator sort of thing. And we do some sort of recurrence and we generate these things. We still have the fact that like these satisfy the same braid and commutation relations. And so we really end up, no matter what path we take in Bruhat order, we get a well-defined family of polynomials. But notice here, now we have this interesting one. Its lowest degree terms are the Schubert we saw before, but now we have this minus x1, x2. So it's a feature, we no longer get this positivity of the coefficients, but we get controlled negativity. So the degree, the signs of the coefficients alternate with degree. So lowest degree terms are positive, 1 degree up is negative, and so on. So since it's controlled negativity, we still can write down some nice combinatorial formulas. Okay, so in particular, there's a Bumpless pipe dream formula, but really it appeared first under the guise of alternating sign matrices in an unpublished preprint of Lascaux. So Lascaux showed us how to write down Grothendieck polynomials as sums of alternating sign matrices. But as we know, these objects are in bijection. Lascaux's formula involved doing some sort of iterative procedure to an alternating sign matrix until you get to a permutation matrix, and then that's the permutation that belongs with the alternating sign matrix. I showed that really you can translate this to BPDs, and the natural permutation you read off is the same as the one you got from Lascaux's alternating sign matrix procedure. What you have to do if you're going to do K-theory, there's a few more subtle things going on. So the weight monomial looks a bit more complicated. So we're going to weight this thing. There's some sort of funny sign based off of the number of boxes that you see, the blank tiles. For each blank tile, we're going to weight it with xi, where I is the row that it's sitting in. And then we also have to pay attention to these upward elbows. They each get weighted with a 1 minus xi, again, where I is the row that that's sitting in. So we take this funny sort of product, and you'll notice if I take like lowest degree terms of this thing, I'm back to the ordinary way of weighting things for Schubert polynomial land. So we have this K-theoretic weight, and maybe you've also already started staring at the permutation and you're like, this is very weird. That doesn't look like the right permutation for this diagram. Is there a typo, Anna? There is not. So I mean, there could be. Look later, maybe. But here, what's going on is we have one of these non-reduced bumpless pipe dreams. So we have these pipes crossing more than once. And in K-theory world, we want to say, okay, if the pipes have already crossed, I don't let them cross again. So as I'm sort of tracing my journey along, I'm going along here, they crossed. When I get here, I say, you are not allowed to cross again. So the 2 has no choice but to take a turn and go out this way. The 1 has to take a turn and go out that way. And so that's the right K-theoretic way to read a permutation off of one of these diagrams. And with that, you get a theorem. So this is, that the Grothendieck polynomial is a weighted sum over bumpless pipe dreams that trace out your given permutation. So here's what our 2, 1, 4, 3 example looks like. So here you'll notice, like, if we take lowest degree terms, we get back to the Schubert polynomial world. And then we have this extra one that has too many boxes. This is the non-reduced one, and we just don't see that in Schubert polynomial land.
So in other words, once you cross, the next time you replace a crossing by a pair of elbows.
Yeah, exactly. And you just want to very carefully work your way from bottom to top and do these local replacements as you found that things had already crossed. Yeah.
So in this case, the reordering this to 1, 4, 3 is basically a cyclic rearrangement, right? It's just 1, 2, 3, 4 shifted by 2 or something.
Oh,
an accident or?
So, wait, I'm not quite understand. Like,
well, the order of numbers. You read from 1, 2, 3, 4.
Yeah, 1, 2, 3, 4.
And on the vertical side, it's still cyclically.
Transpositions, though.
Yeah, so here we had exactly 2 transpositions. So these 2 pipes crossed. These 2 pipes crossed. But generally, you can get any permutation out of this by just letting the pipes cross. Yeah.
So you're replacing this by the thing about the double the bump that was not allowed? Like, so is
yeah.
That, I mean,
so in this one, we could replace this cross with a bump and then just read it off in a very normal planar history sort of way. Yeah.
But so only if, so you fix a choice.
The permutation.
So you fix a choice of where. So the crossing will only happen at the bottom, and then whenever you have multiple crossings, I mean.
Yeah, you can get quite a few crossings going on, and you just like.
So you fix that the crossing is at the bottom, and you replace every crossing above by a pair of elbows.
Yeah. And you just want to like, here I could like label this like 1, 1, 1, 1, 1, and this 2, 2, 2, 2, 2. And then you can do some little local rules like, oh, 1 is less than 2, and so now they need to cross. But at this point now I have this thing is bigger than this thing, so they're not allowed to cross. So that's a very orderly way of doing it. You can also label the crossings with simple transpositions and put a certain reading order on and take a De Mazur product if you like that way of thinking. So there's all sorts of ways to internalize what sort of permutation should I be getting.
Do you know how many terms are there in
No, and I'll say just a little bit more about not for Grothendieck's, but Schubert's later as like a motivating thing. But sometimes there are nice formulas, but generally there are not nice formulas. Okay, it depends. Schubert, there's McDonald's formula, which is lovely, but not very like explicit. It's a sum over reduced words. Okay. All right. So, here there's also a pipe dream version, very similar. The weight monomials look a little bit simpler now. We don't have this 1 minus xi thing going on. We get to just weight these things by looking at where the crossings are, like we were doing, and then we ensure that we're alternating in sign with degree. And then here, like you'll notice this one has like a whole bunch of crossings. So it's like, okay, we crossed once here, we don't allow this crossing, don't allow this crossing. So you can get very complicated multiple crossings going on. But this is an example, again, for 2, 1, 4, 3. Before we had just 4 objects, but each object was contributing a lot of monomials. Now we have 7 objects, and each contributes a single monomial. Okay. So I should also say this sort of enters the vertex model world in that different groups have given lattice model proofs of these formulas, both for the bumpless pipe dreams and for the pipe dreams. And so there's really some nice integrability ways of thinking about these formulas. Okay, so a few questions that people have about these polynomials. We're interested in, we have ways of writing them down, but we're interested more generally in what's the structure of the monomials that we're seeing? What sort of combinatorial properties do they have? So the big one in Schubert calculus, which I won't really, I'm not multiplying anything, but we want to know nice ways of multiplying these polynomials and nice rules for multiplying these polynomials that generalize the Littlewood-Richardson rule for sure polynomials. That's a major motivation in developing combinatorial understanding of these families of polynomials. So that's just this here. Take two Schubert polynomials. You have a basis. You can expand in this basis. You get some structure constants. They're positive. What do they count? Here, controlled negativity, what does this count? So there's also, this is the question of specializations. If you plug all ones into your Schubert polynomial, it's saying how many reduced bumpless pipe dreams or reduced pipe dreams are there for that Schubert polynomial. And there's this question of, or really a conjecture of Mirzan-Smirnov that says this value over permutations in Sn is biggest on layered permutations. So these are permutations that sort of as a block matrix look like you're taking a bunch of longest permutations in these little blocks and putting them along the block diagonal. So there's some asymptotic understanding of the situation and what goes on with layered permutations in particular. But yeah, this conjecture, it's sort of simple to state, but has remained elusive. So can you better understand, how many monomials there are as a start and which permutations attain the maximum? There's also been the study of Newton polytopes. So Monocle, Token, and Young, they looked at basically all your favorite polynomials from algebraic combinatorics land, and they made a bunch of conjectures about these polynomials, saying that they have this saturated Newton polytope property. So saturated Newton polytope, you basically take your polynomial, you plot its exponent vectors, and you take the convex hull of that. And it's saturated if any integer point in this polytope appears as an exponent vector in the support of the polynomial. Here, this example is too small. I just chose it because I could draw it successfully. But this one has no interior integer lattice points. But if it did, for this to be a saturated Newton polytope, it had better appear in here. So their conjecture was proved for single Schubert polynomials by Fink, Mézeros, Saint-Dizier. Symmetric Grothendieck polynomials, there was a proof of Escobar-Young. But for general Grothendieck polynomials, I think it's still open. I'm looking at the, okay. Pauline is nodding vigorously, so. Good academic siblings, okay. There's also been more recent conjectures about the poset of monomials which appear in the Grothendieck polynomial. So you can just take this poset by really divisibility, and they have a series of conjectures ranging from, okay, if I have a monomial that's not of top degree, then I can climb up in this poset. So I can find something that it divides that's also in the support. Or I can climb up by exactly one step. There's something 1 degree higher. Or if I take two monomials in the support, everything that is in between them, here x1, x3, x1 squared, x2, x3, I should expect to see any monomial that sits between these actually inside of the support. This is different than saturated, this is the Newton polytope? I believe so, but I think it's inspired kind of by that family of, just trying to better understand which monomials are actually showing up in this thing. We have the combinatorics, but there's something subtle about moving from our pipe dream or Bumpless pipe dream formulas to really attack these conjectures. It's been proved in special cases like vexillary permutations, but there's, and very recently inverse fireworks permutations, Tianyi, but there's other things to, other cases to be attacked. Okay. So this circle of problems, this led me to think a lot about like, how do I understand the supports of these polynomials? And in particular, can I understand them by like going back and forth between Schubert world and Grothendieck world? Maybe I can try to change bases to understand the structure of these polynomials. In particular, what it lets us do, if you have a really good understanding of how Grothendieck's expand into Schubert polynomials, then you can group a whole bunch of monomials into one chunk. And so like you can think about the Newton polytope of a bunch of Schubert polynomials and then try to think about how you glue them together. So I'm not claiming any progress in any of these circle of problems, but this is just an initial step at trying to better understand these supports. And that's some of the motivation. Okay, so we're going to change some bases. Changing bases. Okay, so the first formula that I'm going to tell you, or the first two formulas, we're going to go Grothendieck-Schubert and Schubert to Grothendieck. These are due to Leonard and Lascaux. And if you look at their papers, they appear in terms of these triangular arrays. But the triangular arrays, if you like shove them to one side and flip things around a little bit, they are pipe dreams. So I'm going to give you the pipe dream picture, but if you go to the original paper, it will not look quite like this. But here's a recipe. Here's what you do. You take a pipe dream. Any pipe dream could be reduced, not reduced. And you make some little replacements. So above the main anti-diagonal, you change pluses to kind of these upside down bumps. You change these bumps to crosses. So I've done that replacement here. I'm highlighting the crosses to really make them pop. And then you like take away this sort of boundary thingy, and then you do gravity. You just let them fall. So gravity. Now you start to stitch them back together into a pipe dream looking thing. But this pipe dream is now upside down. But I just call this thing a co-pipe dream. It's basically a pipe dream flipped upside down, but it is convenient for this story to leave it flipped upside down. And then when we're reading off a permutation, we label 1 through n, and then we see where the pipes go. And if this was like a flipped upside down pipe dream, I would read in this way. But I'm going to actually want to read this way. So the permutation associated to this is 2, 3, 4, 1. So it's W naught of times like the permutation of the flipped upside down one. W naught's either probably on the right. Okay. So the theorem of Leonard is that we can expand the Grothendieck polynomial in terms of Schubert polynomials. We have this like controllable sign, some controlled negativity, based off of how much bigger V is in Coxeter length than W. We get these coefficients times some Schubert polynomials, and the coefficient counts pipe dreams for W with co-pipe dreams that are reduced and trace out the permutation V. So let's unpack that with this example. So this is what Leonard's, and like 1999. This has been around for a bit, but not phrased quite in this way. So here I have written just some of the pipe dreams for W, not all of them because there's a lot. And notice they need not be reduced. And what I'm going to do is I'm going to take their co-objects, and then I do, the flip and gravity and all that. And then I look for, the co-objects that are reduced. So in the picture I've drawn, I've only drawn the ones with reduced co-objects. I read what permutations I get, and then those are telling me the Schubert polynomials in the expansion. Okay. So Lascaux gave us the other direction, gave us Schubert to Grothendieck. And what's wild about this formula, and I think a lot of people don't know this fact, but Lascaux, 2004, Schubert polynomials expand positively in Grothendieck polynomials. So Grothendieck polynomials have all these signs, And somehow, like, all the signs cancel perfectly to just get this positive expansion into the basis of Grothendieck polynomials. Or, yeah, Schubert to Grothendieck. So here, it's a similar looking formula. We get these coefficients B, W, V. They count reduced pipe dreams for W with co-pipe dreams that trace out V. So the co-pipe dreams don't need to be reduced anymore, but we're summing only over reduced pipe dreams for W. So here's what this looks like here, and again, a positive expansion into Grothendieck polynomials.
But that's not so, I mean, okay, I did not know this fact, but that's not so surprising, right? Because you have this, you're inverting a lower triangular matrix, basically.
Yeah, okay, so thinking, yeah. But like, if you, yeah, it's more just like, I think the surprising part for me is there's all this geometry, and I don't know if anyone knows any geometric reason this should be true, just a priori.
Like, how did you ever map from cohomology to K-theory?
Yeah.
Then maybe that's a real question.
Yeah, and so, yeah, any geometers out there, like, why is this? But yeah, it always, maybe we're just bad at changing bases with matrices, but people tend to be surprised when they learn this.
I mean, I did not know this.
Yeah. Okay, another cool upshot from this formula, which I also find a little bizarre, but is just how this formula works. The monomial and Grothendieck expansions of Schubert polynomials have the same number of terms because we're summing over essentially the same objects, but here we do this flip, blah, 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 to read off the permutation, but same number of terms in the expansion. So,
whereas on the previous slide, there was some other
yes.
clause, right? You need something to be
Yeah.
reduced that wasn't necessarily.
Yeah, you're summing over all pipe dreams, possibly not reduced. And then, yeah, co-pipe dreams must be reduced. So this.
But on the other side, for Lascaux's theorem, you
Yeah.
want only reduced pipe dreams.
Yeah, you sum over reduced pipe dreams, but the co-pipe dreams are allowed to be non-reduced.
So then the number of terms is not the same. Because you
Oh, exactly. The number of terms is not the same. That's what Ben was.
But then what is this?
Oh, this, sorry. We're summing over reduced pipe dreams for W, and then we're taking all of their co-pipe dreams.
No, I understand that. No, I was saying, but what is the cool upshot saying? That they have the
Oh.
same number of terms.
Yes.
The monomial.
Yeah.
Okay.
Schubert to monomial and Schubert to Grothendieck have the same number of terms. Yeah. Like thinking of the Grothendieck as just one unit, one entity. Yeah.
No, but that's what I'm confused by. You're skipping pipe dreams which are not reduced, right?
Yes.
So then there are more monomials that you're skipping.
So here, like I'm saying, like there's 3 monomials in this Schubert polynomial, and there's 3 Grothendieck polynomials in this sum.
But there could be more which are.
No, that's not how the Schubert polynomial formula works. We just sum over reduced pipe dreams to get the Schubert. But there's too many polynomials, and mathfrak S and mathfrak G to me look too similar. And yeah, maybe that's why, yeah. People I know, like they tend to write bars over all the K theory and then just like, yeah, maybe that's better. Okay, cool. So that was pipe dreams. I really like bumpless pipe dreams, so like, what about bumpless pipe dreams? So I'm going to present new formulas for changing bases with bumpless pipe dreams. So what do? What's the right co-object? Well, it turns out we made this choice for bumpless pipe dreams to start from the 6-vertex model, take the arrows that point left and down. We could just as well take the arrows that point left and up, and this gives us our co-object. And so we just label 1 through n, we then trace out where things go, and again, I want to read this word top to bottom. Even though if it was like a flipped upside down pipe dream, I would read the word in the other way. So this is this co-object in this case. And first I'll give you Grothendieck to Schubert. It looks like the text of the theorem is like identically the text of Leonard, basically. You just replace, take pipe dream and replace it with bumpless pipe dream. So we take the bumpless pipe dreams for W, possibly reduced, not reduced. We take the ones that have co-bumpless pipe dreams that are reduced and trace out V, and this tells us the coefficient. So here, well, we get the same expansion as before, but now as a sum over these objects instead. So here's just an example of some more things that can happen. So here I can take this object, and then this one's not reduced, so it's not contributing to the sum. It's certainly possible to get multiple bumpless pipe dreams that trace out the same permutation. So here we get a 2 as a coefficient on this Schubert polynomial. Okay. And then there's like the version of Lascaux's theorem is also like take out the word pipe dream, put in the word bumpless pipe dream, and it's the same thing. But now as a sum over bumpless pipe dreams. So we take just reduced bumpless pipe dreams for W, and we take any bumpless pipe dreams that come our way. And we sum over these things, and again, we get this positive expansion, Schubert to Grothendieck. Okay. So more examples. Yeah, here we have like so what's funny with bumpless pipe dreams is vexillary 2143 avoiding permutations, they only have reduced bumpless pipe dreams. So here we get to just sum over these things, and then we get this sum with the co-objects. Okay, so let's compare the pipe dream formulas and the bumpless pipe dream formulas. This is a big meta slide with all the information for 2143 right there. It's a little tiny, sorry. But here I've listed all of the pipe dreams for 2143, all 7 of them. And I've listed all of the co-objects. These first 3 are the reduced bumpless pipe dreams for 2143. So here, like, we take these reduced ones, we sum over these 3 things, and we get this expansion. Or we can look at the ones with co-pipe dreams that are reduced, and we sum over those to get Grothendieck to Schubert. So in principle, to write down Schubert to Grothendieck, it's always easy. You get to sum over just reduced things. But to write down Grothendieck to Schubert, you really kind of have to like go search through all the pipe dreams and then throw away a bunch of stuff, at which point you might as well have just kind of written down the Grothendieck polynomial. But anyway.
Sorry, do you ever get multiplicities in these formulas?
Absolutely. There was this one. Yeah. So there can definitely be multiplicities. I'm doing kind of small examples, and so, well, this small example we see multiplicities, but yeah. Okay. So this is, I've just been using 2143. It's my favorite example, and it's an involution, and I shouldn't use it so much, but I do. Okay. But in terms of a bumpless pipe dream world, well, we had 7 pipe dreams to shuffle through. We only have 4 bumpless pipe dreams to worry about, because each bumpless pipe dream is contributing several terms to K-theory. As many, like the upward elbows are giving us like multiples of 2 for monomials. Okay, so here, like, we actually didn't have to throw anything away for our Grothendieck to Schubert expansion. But generally, we do have to throw some things away still. But there's just less objects floating around, so that's kind of nice. Okay, so one thing I haven't really looked at very much, but if it intrigues you, I'm wondering which permutations have the property that all of their co-bumpless pipe dreams are reduced. Is there a nice characterization of permutations for which you don't have to throw anything away when you do the Grothendieck to Schubert expansion? For pipe dreams, this question doesn't really make sense because this only happens for dominant 1-3-2 avoiding permutations. So pipe dreams, you will just always have to throw stuff away if you're outside of this dominant case. Okay, so in the time remaining, I'm going to just give you a little bit of the idea of the proof and why these formulas really look so similar. Gao and Hong, I mentioned this before, they gave a weight-preserving bijection between reduced bumpless pipe dreams and reduced pipe dreams. Here, we're going to just use the column version, so the version with those y's from way too long ago in the talk. But basically, we want to make sure that this bumpless pipe dream has the same number of blank tiles in each row as this pipe dream that it belongs with has crosses in those. Sorry, I said row when I meant column. So column weight preserving. So if a bumpless pipe dream and a pipe dream belong together under this column weight canonical bijection, I have shown that the permutations of the codiagrams are preserved. So these codiagrams have the same permutation. And that's really the connective tissue between the two versions, the pipe dreams and the bumpless pipe dream formulas. So how does this proof go? It's like a little bit technical, but the idea is there's a very simple recurrence on pipe dreams called cotransition due to Knudsen. And Knudsen said, well, I can take a Schubert polynomial, multiply it by a specific variable, a very special variable based off of sort of the shape of the permutation, and I get this nice positive expansion of other Schubert polynomials. And the idea is to kind of look for the first place in a column that I have a bump, and that bump is going to be present in all these diagrams, and I'm just going to change that bump to a cross in all of them. And when I do, I can group things nicely into Schubert polynomials. So like these two are 2, 4, 1, 3 piece. This one is 2, 3, 4, 1. And there's a very explicit way of writing it in terms of like transpositions and indices, but I'm not going to do that. I'm just going to show you this picture. So easy recurrence on pipe dreams. They're like this drags along for the ride by the canonical bijection a recurrence on bumpless pipe dreams, and that is the flipped pipe dream changes in a very predictable way when you do this. If you're adding a plus over here, you are removing a crossing in the flipped thing. And the permutation can sometimes just not change. So if like these things were already in order, they're not going to change. If these things are out of order, they're going to flip. Okay, so cotransition on bumpless pipe dreams, it's harder to see. And thankfully, work of Daoji Huang tells us how to do this. So you do sort of this like almost insertion algorithm on bumpless pipe dreams where I say, hey, I'd really like a new box in column 1. And there's like this elbow in the row or in the column preventing me from doing that. So I'm going to try to like bend this over. And when I do, oh no, I got a bump. What a disaster. I don't want a bump. So I would change it into a crossing. But when I do, changing that into a crossing would have made a double crossing, so now I need to swap that cross and the bump. And there's a whole thing. And you like keep going and iterating until you've resolved to an honest-to-goodness bumpless pipe dream. And now this bumpless pipe dream has the property that it has exactly one more box in column 1 than it started with. And so this insertion procedure is compatible with the canonical bijection because that's what the canonical bijection does. Anything that respects multiplication gives us the same bijection, basically. And then the technical fussy part is looking at what happens with the co-bumpless pipe dreams as you go. But you can sort of show that you can group some of these moves into permutation preserving sort of things. And then maybe at the end you get an extra little flip, an extra little transposition that's mirroring what's going on the pipe dream side of things. Okay. So that's the idea of the proof, that this canonical bijection is the connective tissue between the two types of formulas. So further questions, especially for this crowd, is there a nice proof that like avoids this canonical bijection and just does things directly either on pipe dreams or bumpless pipe dreams using vertex model techniques? And then can you push these formulas to give expansions of like double Grothendieck polynomials, x's and y's, into double Schuberts? I'm imagining that would be hard, but I don't know. Is there anything to be said in that direction?
So for your second
Yeah.
question, that completely breaks your proof technique, right?
Oh yeah, like, yeah. My proof techniques can only see x variables, and yeah. But yeah, what do these expansions look like? I don't think people have really studied them. It might be an odd thing to study, but you could certainly try. Okay, and that's it. Thank you.